In this project, we're talking about discrete structures, a foundational area of mathematics used in computer science. Unlike calculus, which deals with continuous change, discrete structure focuses on distinct countable elements. These include things like logic, sets, functions, relations, graphs, trees, and combinatorics. They allow us to model and solve real-world problems by breaking them down into manageable, logical components. You can think of them as the rules and tools behind everything from writing a sorting algorithm to designing a social network. Discrete structures are crucial in fields like programming, cybersecurity, data analysis, and artificial intelligence. For instance, logic forms the basis of programming languages. Graphs are used to represent networks, whether it's roads, internet connections, or friend groups. Combinatorics helps with calculating probabilities, optimizing choices, or generating all the possible outcomes in a scenario. Without these structures, many of the systems that we rely on today wouldn't work efficiently or even correctly. Let's bring this to life with a simple scenario. Imagine standing in front of your closet trying to decide what to wear. You have a few shirts, a couple pairs of pants, and some shoes. You want to know how many unique outfits you can make from what you already own. This is a classic example of combinatorics problem. Each category, shirts, pants, and shoes, represent a set. We want to calculate the numbers of ways we can combine one item from each set. Here's the problem. You have 3 shirts, red, blue, and green. You also have 2 pairs of pants, jeans, and shorts. And for shoes, you have sneakers, sandals, and boots. The question is, how many different outfits can be made by choosing 1 shirt, 1 pair of pants, and 1 pair of shoes? This problem might seem small, but it demonstrates how quickly combinations grow as we add more choices. It's this kind of thinking that's applied when designing user interfaces, product options in e-commerce, or testing all of the paths in the software system. Fortunately, we wrote a Python program to solve this exact problem. It uses a iterstools product function, which is based on the Cartesian product, another concept from set 3. The code defines 3 lists representing the sets of shirts, pants, and shoes. It then calculates every single possible combination by multiplying the sizes of the sets. This program uses combinatorics and set theory, 2 fundamental areas in discrete structures. It prints all of the alpha combinations and gives us the total count. This method not only solves the problem quickly, but is scalable, meaning it can handle a lot more items just as easily. Let's break down what the Python code actually gives us and how to interpret the results. The code takes 3 lists, 1 for shirts, 1 for pants, and 1 for shoes. Each list is a simple collection of clothing items. Using itertools.product, the program calculates every possible way to choose 1 item from each list. This is known as the Cartesian product of the sets. The result is a list of tuples where each tuple represents a complete outfit, 1 shirt, 1 pair of pants, and 1 pair of shoes. Now, let's talk about the output. The program finds 18 total combinations. This makes sense because we're multiplying the size of each category by 3 shirts times 2 pants times 3 shoes, equaling 18 outfits. This is a fundamental concept in combinatorics. If there are n ways to do one thing, m ways to do another, and p ways to do a third, then there are n times m times p total ways to do all 3. The output lists each outfit clearly. For example, outfit 1, red shirt, jeans, and sneakers. Outfit 2, red shirt, jeans, and sandals. Outfit 3, red shirt, jeans, and boots. And it continues through every possible combination. To make this more intuitive, imagine each clothing category as a level of a decision tree. At the top level, you pick a shirt. From each shirt, you branch into the possible pants. From each pair of pants, you branch again into the shoes. This tree visually expands as the combinations grow. Each complete path from the top to the bottom represents 1 unique outfit. The code automates the entire process for you in a matter of milliseconds. Visually, you could show this by animating 1 shirt being paired with all pants, then one of those pairings being matched with each shoe option. It helps the audience connect abstract math with something they can do every day, like getting dressed, while showing how fast and powerful computational thinking can be when backed by discrete structures. What normally seems like a simple question about clothes is actually a gateway into a powerful world of discrete structures. Whether you're trying to count combinations, design a circuit, or write a program, these concepts are always at work. They help break down complexity and give us tools to make decisions, optimize systems, and build smarter software.